Okay, last time we were talking about how surface integrals are just an extension of line integrals. They're really almost the exact same thing. So, and then there were two. We know there's two kinds of line integrals, right? So, there's a line integral of a multivariable function, and so then we have the analogous type of surface integrals. So, with these line integrals of multivariable functions, we had a function of two variables, and um, for the surface integral, then that was a function of three variables. And then we parameterized the single variable, or we parameterized the curve in one variable t, so that's our r of t. And then we saw with these surface integrals, we know that surfaces are parameterized as two variables, generically u and v. And just like line integrals, we rewrote the whole integral in terms of t. We rewrite the whole integral in terms of u and v, both the function and we saw this common element here where it's the derivative of the vector function, the magnitude of it. Well, in this vector function, there are two derivatives. So we take the magnitude of the cross product. And remember that was these areas of these parallelograms that are like these flat elements that are reproducing the surface, just like ds. These were little segments that reproduce the curve. So we have this kind of very, very strong parallelism with these. And then there's another kind of, we know the other kind of line integral is a line integral of a vector field. So that's what we're going to be talking about today. So this is a review from last time. So now, I don't have a pretty slide for you, but I can still do the job pretty well. So now we're talking about line integrals of vector fields. Okay, so the first type of line integral was a line integral of a multivariable function. A line integral of a vector field was of this form. And so now we've got some path, maybe even in space, it could be in the plane or in space, through a vector field f like this. So that path is through a vector field. That could be like a fluid field or electromagnetic field. And what are we doing now? So now we are taking f dot dr. So dr would be little vectors parallel to the curve. Little drs would be, because we know that c is defined, r is a function of t. So dr would be like little parallel vectors. And so by doing f dot dr, we're taking the components of f in the direction of dr. So whatever the vectors are along c, we want the product. We want as much of those vectors as is in the direction of the curve, but then times an infinitesimal length of the curve. So for instance, if at this point on the curve we had this vector here, then we want dr times this component, which is in the direction of the curve. That's what the dot product does, right? It gives us as much of f as is in the direction of this, which is the tangent to the curve. So maybe that f dot dr then is going to be some little amount of work. Like if this is a force field, and this c is an object moving through that force field, then this computes a little bit of work by taking the part of f in the direction of the curve dot dr. And we know to do those, we're going to rewrite f in terms of t. And then the dr vector is what? Dx dt dy dt, or x prime, y prime, z prime, dt. So that's review. That's our line integral vector fields. So we have surface integrals in vector fields. And again, you have strong parallelism. Really a strong analogous situation here. So now we have a double integral of s, and it can be f, and again dot, and it's going to be that same vector we talked about on Monday, but it's actually the vector now, not just the magnitude of it, ru cross rv, and then du dv. This whole thing is the d capital S vector. Also, in the web work, I think they use d capital A. And that includes the du dv. So f dot ds is really what I should have written here. So that is like this left side over here. And then what is the dot ds? This is ru cross rv du dv. So let's talk about what's going on here. So we have some surface like this. And we know that surfaces can be defined in two variables, two parameters, right? Curves defined by one parameter t. Surfaces, we parameterize those as two variables. And that's in a vector field. That surface. So we know that the reason we need two variables in a surface is because there's kind of like, those would be like values of, say, constant u along the surface and then constant v along the surface, right? There's two degrees of freedom on a surface. That's why we need two different variables. So this, like, maybe these are constant v values this way and constant u values this way. So ru and rv, these partial derivatives, would be, so for instance, for this little element right here, it's kind of like our parallelogram element, ru would be tangent to a curve of constant v value. So maybe this is ru. And rv would be tangent to the trace of constant u value. So it's kind of getting hard to see there. That's better. So ru and rv would both be parallel. They'd be orthogonal to each other and parallel to the surface because they're derivatives. So they give like tangents, a tangent vector to the traces that form the surface. So then now we're actually using the vector, not just its magnitude. So what is the cross product? The vector cross product. What does that represent? Remember what you get when you take the cross product of two vectors.
The vector that's orthogonal to both of those vectors.
That's right. So if it's orthogonal to both those vectors, what is it also orthogonal to in this situation?
The surface.
Yeah, so we're going to get an orthogonal vector. Ru cross Rv is going to be orthogonal to the surface. So now on that surface, you have all these vectors of the field f. And when you take f dot, this is a function of orthogonal vectors to S. So as u and v vary, this ru cross rv gives vectors orthogonal to the surface. And if you take f dot that, then you're looking at the component of f at that point in the surface in as much as it's in the direction of orthogonal to the surface. So With a line integral, it was the parts of f that were parallel, right? Dr. Dr is parallel to the curve, but this RU cross RV is orthogonal to the surface, so we're taking as much of f as is orthogonal, or is in the direction of the orthogonal vector. So if your f vector was like, if your f vector was like this at that point on the surface, then you're going to take the component of that in the direction of orthogonal to the surface. And then the dot product within kind of an infinitesimal or very small vector will give a very small, so f dot, this is the product of the magnitudes in as much as it's in the direction orthogonal to the surface. And so then what we're taking is like, then we're going to accumulate that over the surface. Accumulate all those parts of f dot dA or ds. Accumulate those all across the surface. So what we get then is what's called flux, which is net flow rate. It's actually evaluating how much, according to f, how much goes through that membrane, right? So that's why we care about the orthogonal direction. Whatever is parallel to the surface, whatever parts of f are parallel to that surface, it's just, there's no flow through, right? The only flow through is the parts of f that are orthogonal to that surface. So that's what we're accumulating here by taking the dot product and then accumulating that across the surface. So we get net flow through the surface of f, and that's called flux, or net flow rate actually, and that's called flux. All right, any questions on that? I got a kind of a little illustration to kind of reiterate that, but before I erase what I just said, any questions on that?
So this is kind of how Calc 3 is, I guess, used in, say, something like electromagnetism with Maxwell's equations, right? Like with electric flux and all that.
Mm-hmm. Yep. Yeah, flux is like flow through a surface. So then we only care about the direction orthogonal to the surface. Therefore, this vector here. So you take the components of f in the direction of perpendicular to the surface. So I think this next, I have a little animation here that really helps to see that. In terms of calculating the flux, this is our equation. And that takes a fair bit of work, as we'll see here shortly.
Professor?
Yeah.
So the final value of this integral, it gives the flux, so the net flow rate.
That's right.
Okay, so it's not just a value, it's actually a rate itself.
I'm sorry? What was the last thing you said?
No, I guess I'm just trying to understand why it's a rate and not just like a value itself.
Yeah, that's kind of, so you can just think of it as net flow. It is a rate, but if you just want to think of it as like the amount of flow through because flow itself is a rate, right? It's like how much per time or something, right?
Okay.
But if you just want to think of it as the amount, don't get hung up on the rate part of it. If you just want to think of it as kind of the net flow through the surface, that's good enough for our purposes. All right. So let's take a look at this. So here is a surface in a field. So there's a vector field. We got this surface. So if we want to talk about the flux, or the surface integral for this surface of this vector field, then first of all we care about is the vectors that are at the surface itself, right? So only the vectors that are for the points on the surface itself are the only ones we care about. So that's an illustration of just the vectors of this field that are associated with the points on our surface. But then all we care about those vectors are the the components of those orthogonal to the surface, so the blue ones. So whatever of those red vectors is parallel to the surface contributes nothing to the flow through the surface. Only the components of those vectors orthogonal to the surface are what contribute to flow through. Now those vectors will be greatly diminished when we dot them. We're dotting them with ds, which is making things very small. But this is just an exaggerated kind of picture of that. So then in the end, calculating the flux is just really looking at those blue vectors. And it's a net value, so you see that most of the flow is in the positive x direction, but it will be reduced by whatever flow over here is in the negative x direction. So these are the components of the vector field. These are the components of the vector field, orthogonal to the surface, and then the ones that are on the surface are orthogonal to the surface. And that's what we care about when we're calculating the flux. All right, so let's look at some examples here. All right, so let's try this. So let S be the part of the plane that lies in the first octant, oriented upward. We're going to find the flux of this vector field across the surface S. So our flux is that's our generic formula for the flux, which is totally parallel to a line integral of a vector field, right? F dot dr, single integral F dot dr. This is so here we go. So first we have to parameterize the surface. So we have, so let's see, when x and y and 0, z is 2. When x and z and 0, y is 2/3. When y and z are 0, x is also 2/3. So they're talking about here is our surface. That's S. Okay, so S is this triangular patch of the plane lying in the first octant. So we want to parameterize that. So remember, when you parameterize a surface, you have to choose carefully, choose your two variables carefully. You get two variables to express every point x, y, and z in R3. So for this particular situation, what's going to be our best choice for choosing our two variables?
X and Y.
Yeah, so this is one of those situations where we can choose x and y, and then z is easily determined because essentially we have z as a function of x and y here. So we'll have x, y, and what does z equal?
2 minus 3x minus 3y.
That's it. So remember, this is the easiest case for parameterizing surfaces. When you have a function, z is a function of x and y, then you can just let x and y be your two variables and use the formula for z as the z component. So that will get all points on this plane. X is x, y is y, and z is always this. Okay, so we're going to do two things with that. We're going to rewrite function f in terms of that, because this is, again, all we care about is the points on the plane. This tells us all the points on the plane. And then we're also going to find this cross product. So that cross product ijk and then say rx, ry is the cross product of the partial derivatives. So we're going to do the partial derivative with respect to x. What are they here? We got 1, 0, and -3. Partial derivative with respect to y is 0, 1, also negative 3. And so my Rx cross Ry is, so down to the right we get 0 for the I component, down to the left minus negative 3, so positive 3. Check my math. Okay, the J component down to the right is 0, down to the left minus negative 3 is also positive 3. And the K component down to the right is 1. So that's a nice, easy cross product. Resulting vector, just 3, 3, 1. Okay, so now you notice that it says that this plane, it says oriented upward. So what that means is when you talk about calculating the flow through a surface, you need to define what positive flow is. Which direction is positive flow, right? Because there'll be two directions of flow. So this is telling you that upward orientation is positive flux. That the orientation is always indicating the direction that the flux will be positive. So when you find these perpendicular, right, these vectors are all orthogonal to the surface, that has to agree. Your cross product has to agree with the orientation. So we got the cross product 3, 3, 1. Does that agree with upward orientation of this plane?
Yeah.
Because what is it about this that tells us we have upward orientation looking at these vectors? So 3, 3, 3, 3, 1 would be, all the vectors would be like this. And it's a plane, so it makes sense that they should all have the same vector. So what is it about this that we confirm that we have upward orientation?
Is it the positive z component?
That's right. Z is greater than 0. So z greater than 0, that agrees with the fact that we have upward orientation. And so we like this this Rx cross Ry vector because it's in line with positive orientation, which is upward or kind of up and outward, like out toward us in the first octave.
What could we do if it did not agree?
Yeah, we'll see an example of that. So we'll see an example. Yeah, so it's like if we did Ry cross Rx, then what would we have gotten for this vector?
Would it have been the negative values?
Yeah, if you did Ry cross Rx, you would get negative 3, negative 3, negative 1. So that would mean those vectors are the ones like pointing into a little bit downward and into the screen. This way. So that's supposed to be pointing back into the screen, not forward. It's hard to get that perspective. Okay, but those are pointing back into the screen and a little bit down. So that direction would not agree with this, and we'd have to flip it and do Rx cross Ry. Okay, so now we got everything we need. We can rewrite our surface integral. So what is f? F is 1, 3, 3. And then if we needed to, that vector field could be a function of x, y, and z. And we're going to use our x, y, and z on the surface to rewrite that. And then dot Ru cross Rv, which is what, 3, 3, 1. And then dx dy, or whatever. So however we want to do this double integral. So we can write down dx dy, and if we want to change it, we can. So now we have the double integral of what? 3 plus 9 plus 3. And how do we do this? Well, we need to get the projection. This is now our kind of like our triple integrals. We need the projection of that surface into the xy plane. So we found out before that these points are 2/3 and 2/3 here. So this is y equals 2/3, x equals 2/3. So our double integral is going to be the limits of integration are according to how that plane projects into the xy plane, which is like this. And so what is this? Y equals 2/3. Looks like minus 1x, right? Slope of -1, y-intercept of 2/3. So how do we want to do this? Do we want to do, so now we have our choice. We have a double integral. We could do type 1, type 2, or polar. So I've written this as y equals 2/3 minus x, so I think it'd be easiest just to do type 1. So type 1 means go from bottom to top, 0 up to 2/3 minus x. And then that from all those bottom to tops starting at 0 to 2/3. And for time's sake, I'll let you finish that. So this is the flux or net flow of this field through that surface. Questions on this example?
Yeah, Professor, when you like set up the problem and then made the definition of the plane, like parameterized it, then you said that, and you drew arrows like from the definition of R to both like F and RU cross RV. Doesn't F come from the problem, not from our like?
Well, we're gonna use, but yeah, yes, but we're gonna use the parameter. So this is oftentimes functions of x, y, and z, not constants like this. We have to rewrite. We're gonna have to rewrite all those components of F in terms of our points on the surface.
Oh, okay, yeah.
So you remember doing that with line integrals, where you had to rewrite the F in terms of t, and t was your parameterization of the curve. So it's the same thing.
Yeah,
but
I forgot how F relates to the parameterization once we.
Yeah, we just all we care about are the points of F that are on the surface, so we can use the ordered triples of the surface, substitute them in for F.
Okay, thank you.
Yeah, sure. Other questions on this one?
Professor?
Yeah.
So for the 3 plus 9 plus 2, it comes out, it's like, is that 3 like I plus 9j, or?
No, it's a dot product. It's not a vector anymore. It's a dot product, right? Dot product gives a scalar.
Okay, so we can just add them up, right?
It's a dot product. So x components multiplied, y components multiplied, z components multiplied, and dot products as you add those together.
Okay, thank you.
Yep. Other questions? Okay, let's look at another example. This one. All right, so here our vector field is x, y, z, and we have a cylinder x squared plus y squared equals 4. Okay, so we need to, and then let's sketch that. And then it looks like that's going to be between x plus y plus z equals 3 and x plus y plus z equals 8. And so we're going to have this cylinder, right, is parallel to the z-axis. Those should be parallel. So something like that. So this is x plus y plus z equals 3. X plus y plus z equals 8. but those are just, that's just cutting it off, right? We're not, those aren't, right, so all we care about is the flux through the cylinder. And these planes are just telling us where to stop and start the cylinder. So they're not part of the surface. They're just telling us start at x plus y plus z equals 3, end at x plus y equals z equals 8, and find the flux out that cylinder. So now we need to parameterize this. And we want to choose very wisely, like we've worked on. What two variables are we going to choose to parameterize a cylinder? X squared plus y squared plus equals 4. So how do we parameterize this?
All right.
What was that?
R and theta.
Okay, r and theta. So r and theta would be for, like, you know, every distance r, a variable r, and then a theta going around like that. Is that what we've got here? We need all these. So do we need to, yeah, do we need to take into account lots of r's here?
No.
No. R is always what?
2.
R is always 2 for every point on the surface. So we're not going to use r as a variable because r is always 2. So for a given circle, we just need one variable, say for a given circle here, which would be what variable? Can we get every point on a circle?
Theta.
Theta, okay. And then, but then we need to get all circles, right? We need to get points on all circles at all heights. So our other variable should be?
Z.
Z. Someone said Z and theta before, and they were right. So Z and theta are what will parameterize this surface, because theta will get us every point around a circle, and then Z will get us every circle. That gives us every point on the cylinder. Okay, so we want to write all ordered pairs on the surface, or triples x, y, and z, as, in terms of r and theta. Sorry, z and theta. Z and theta. So what are x coordinates on these circles and y coordinates?
2 cosine theta, 2 sine theta.
Right, radius is 2. Theta gets us all the points around the circle, so 2 cosine theta, 2 sine theta. And then what is z?
Is it just z?
Yeah, just z. That's why advantage to picking z. So this defines every point on that cylinder. Okay, so we're ready to write the, and so now we gotta rewrite our vector function in terms of x, y, and z, and we also got to figure out what the cross product is. So let's do the cross product here. So do I, j, k. And we're going to do, say, r, we can do partial with respect to z and the partial with respect to theta of our vector function. So partial with respect to z, it looks like it's going to be 0, 0, 1, partial derivatives. With respect to theta, it looks like minus 2 sine theta, 2 cosine theta, and 0. So now that vector is going to be, it's like I, down to the right is 0, down to the left minus 2 cosine theta. J down to the right is minus 2 sine theta, down to the left is 0. And K is down to the right is 0, down to the left is 0. Okay, so now we've got, this is what? This is the function of orthogonal vectors to the surface. We have to check to make sure we have the orientation correct. Oriented away from the z-axis. How do we do?
wouldn't this vector point inwards towards the z-axis?
Yeah, right. So if you look in the first quadrant here, first quadrant, both cosine and sine are positive. So in the first quadrant, you've got vectors like this. Actually, on the circles with radius 2. So your vectors in the first quadrant are like this. And that's actually, so that this orientation is pointing inside, toward the z-axis, inside the cylinder. And that's not the positive orientation. Positive orientation is away. So we should have done what? Instead of RZ cross R theta, to get the right orientation. Yeah, to get the right orientation, we should have done R theta cross RZ, and we know exactly what that will be. We didn't waste any time because we can use our answer to write this one down, which is
2 cosine theta, 2 sine theta, 0.
Exactly. So now that's what R theta cross RZ would be, and that agrees with a positive orientation away from the z-axis. Vectors pointing out away from the z-axis or the origin if you're in R2. So now we're ready to write our flux integral, f dot R theta cross RZ d theta dz. So we want to write f in terms of our vector function here. So what is f? F is x, y, z. So it's going to be the same as the vector function, x, y, z. Dot the cross product, which is 2 cosine theta, 2 sine theta, and 0. So only coincidentally are we getting the same thing here for the x and y components. And that would be d theta dz. Okay, and so then that equals double integral dot product 4 cosine squared, 4 sine squared, 0. And I'm running out of room here, so I'll take it back up over here. Sorry. So what does this integrand become? 4 cosine squared theta plus 4 sine squared theta is?
4.
4. And then we have d theta dz. And so theta goes from what to what?
0 to 2 pi.
And what does z go from?
3 to 8.
No, not 3 to 8. It goes from this plane to this plane. So what is z here? Z is?
3 minus x minus y.
Yep. And then this one is 8 minus x minus y. So am I on the right track here? Am I going to be able to do it this way?
d theta?
Yeah, because look at my z bounds, our functions are going to be functions of theta. X and y are going to be functions of theta. I got to have that first. So I'm going to have to do dz first. Or else I'll be stuck out here in the outer integral with thetas, and we'll already have integrated with respect to theta. It won't work. So I need to do dz first, then d theta. And z is going to go from 3 minus, what, 2 cosine theta minus 2 sine theta. 3 minus x minus y up till 8 minus 2 cosine theta. It's 2 sine theta. And then from 0 to 2 pi. Okay, again, not that pretty easy to solve from there. Questions on this example?
Why we take r theta rz instead of like we did the first time for 2 cosine 2 sin theta 0?
You're talking about this?
Down. Yeah, bottom here, right?
Here, this?
Yes.
So this is when I did rz cross r theta.
Right, and then we did the r theta cross rz
Right.
at the positive.
Right.
Why are we doing that?
Because it has to agree with the orientation of the surface. The orientation is away.
I didn't see that. Thank you.
Away from the z-axis. So this orientation is all these vectors pointed towards the z-axis. So that was the wrong order of the partials. So I got to put theta first, and then I get the vectors pointing out away, agree with that orientation.
Thank you.
Yeah, sure.
I missed that point.
Yeah, that's okay. Other questions? All right, let's look at one more. Okay, let's do this one. This one's a little more involved, longer. We can set it up. All right, there we go. So we want the flux of this vector field, y5 and minus xz. Through S, which is this. So we have to identify that. So we worked hard at the beginning of the semester, tried to emphasize all these important surfaces and learn about those. What kind of surface is that?
Paraboloid.
Okay, good. At least two of you remember. It's a paraboloid, and then how does that graph?
Opening up in the y direction.
Right, it has vertex at the origin, it opens up in the y direction. And we want that paraboloid only for x squared plus z squared is less than or equal to 9. So there's going to be some point out here where we're going to stop and finish the surface here. So notice that x squared plus z squared, well, that is y. So this is the same as saying for y less than or equal to 9. So this point is 9 right here. So we want only the part of the paraboloid up until y equals 9. All right, so we got to parameterize that. So we want to get all the points on this surface as x, y, and z.
Would we use r and theta?
So we got kind of a couple choices here. Because y equals x squared plus z squared, we might think, oh, let's do x and z. X for x, z for z, and then y is x squared plus z squared. But the problem with that is when we do the double integral, we're going to get the surface projected into the xz plane. And what kind of thing will we get when we project the surface into the xz plane?
A circle.
Well, the circle is just the edge. So we're going to get a disk. And that disk has a circular boundary, which is not going to be convenient with having our variables be x and z. So what variables will be convenient to integrate over this disk?
R and theta?
Yep. So r and theta are going to be the best. So we got our circles are based in the xz plane. So we can do x as our cosine theta, and z is our sine theta, and then what's y? Y is just, for the surface, it's just x squared plus z squared, so it'll be r squared cosine squared theta plus r squared sine squared theta. And what's that?
R squared.
Just r squared, right? Factor out r squared and you get r squared times 1. Okay, so we got our parametrization of the surface, and we've got our function, which we're gonna rewrite our function in terms of this x, y, and z, and we need the cross product. So we're gonna do r cross r theta. Partial with respect to r, cosine theta, 2r sine theta. Partial with respect to theta, minus r sine theta, 0, r cosine theta. Cross product. I will be down to the right, 2r squared cosine theta. Down to the left, 0. J minus, down to the right, it would be minus r sine squared theta. Down to the left would be minus r cosine squared theta. K component, down to the right is 0. Down to the left, minus 2 negative 2 r squared sine theta. What's the y component turn out to be there?
Negative r.
Negative, right, negative r. Factor out negative r. So let's take our orientation. Now we've got the cross product. Oriented in the positive y direction. Does this vector agree with positive r direction? Or positive y direction?
Because we have a negative 1.
Yeah, this is, the value of r is positive, so we're taking the opposite. This is less than 0. Does not agree. Therefore, what cross product should we have done instead?
R theta cross r.
Yep, we need r theta cross r, which is going to be negative 2r squared cosine theta, positive r, and negative 2r squared sine theta. That agrees with the orientation that they want, positive y. So quickly here, we're going to rewrite f. So our flux is going to be, rewrite f in terms of the vector function. So y5 minus xz is going to be, using this right here, so y is r squared. 5 minus xz will be minus r squared sine theta cosine theta. Dot. This one here, minus 2r squared cosine theta, r minus 2r squared sine theta. And then that's going to be dr d theta. Now, it's not r dr d theta because we started, in our parametrization, we started with r and theta. That's our u and v. The time that you include the r with dr d theta is if you're working in rectangular coordinates, you're working in x and y or x and z, and you're making a conversion into polar coordinates. So if you did all the work in x and z, and you had this integral or x and y, and then you want to switch it to polar, then your dx dz would be r dr d theta. But if you start and your parameterization from the beginning is r and theta, then you don't stick an r in there. You just keep it dr d theta.